nuclear physics subject in which the chapter is general properties of the nucleus. This is 7th part of this nuclear lecture series. Topic is Pauli's spin formalism. My Facebook ID is available. If you are interested, you can like this Facebook page www.facebook.com/apniphysics. Website on which you can find similar lectures www.apniphysics.com. Myself, Dr. Sushil Kumar. Pauli's spin formalism. Pauli introduced basically the spin operator sigma that is related to the spin vector S in this way: S is equal to h cross by 2 sigma. Sigma has three components: sigma x, sigma y and sigma z, where sigma x is equal to 0, 1, 1, 0. Sigma y is defined by 0 minus I, 0, and sigma z is equal to 1, 0, 0 minus 1. Now sigma x square is equal to sigma y square, sigma z square, and numerically the value is equal to 1. Sigma square is equal to sum of these components: sigma x square plus sigma y square plus sigma z square, and this is equal to 3 because 1 sigma z square is equal to sigma y square. From the above relation you can see, so sigma square is equal to 3. Now we will analyze this result. So here you can see sigma x square, that is written in terms of the matrices. So sigma x and sigma x, see this is sigma x, this is sigma x, is equal to the unit matrix 1, 0, 0, 1. Similarly you can find out sigma y square and sigma z square. The second part is about the spin. Spin up and spin down, these two different states of the particle is represented by the Pauli spinors. Here alpha and beta are two different states of the particle that basically represent the spin up and spin down. 1, 0 for the spin up, 0, 1 for the spin down. So this is known as Pauli spinors. In earlier slide you have seen S is the spin vector and sigma is the spin operator. So Pauli spinors are what? These are alpha and beta, which represent the two different states of the particle, that is the spin up and spin down. Spin operators are sigma x, sigma y, sigma z, and some mathematical property which is associated with this. This property sigma x alpha, if you take, it gives the beta. Sigma x matrix, alpha matrix, that is spin up. When you multiply these two you will get this result, that is the beta, and beta is the spin down Pauli spinors. And if you take this one sigma y alpha, you will get iota and beta. Sigma z alpha is equal to again alpha. So you have to keep remember these relations, and you can prove these with the help of matrices. Sigma square alpha is equal to 3 alpha, sigma square is equal to 3. So this is equal to 3 alpha, sigma square beta is equal to 3 beta, and these properties sigma x beta is equal to alpha, sigma y beta is equal to minus I alpha, sigma z gamma is equal to minus beta. So these are some properties associated with the Pauli spinors and operators. Now this S square alpha gives h cross square upon 4 into sigma square alpha. You know that S is equal to h cross by 2 sigma, right? When you put this value S square here, this is equal to h cross square by 4 sigma square alpha. Sigma square, you know, that is the 3, so that value is here 3. H cross square divided by 4 into alpha. Now we have to convert it actually in terms of the S spin vector. So this 3 by 4 we can write in terms of 1 by 2 by this way. 1 by 2 into 1 by 2 plus 1. And as you know that 1 by 2 is the magnitude of Sz, right? Spin vector along the z direction. So this is spin S1 by 2. So you can write here this S square alpha in terms of S, that is S into S plus 1 H cross square alpha, and similarly in terms of beta, S square beta is equal to S plus 1 H cross square beta. And now S Z alpha is equal to H cross by 2 into alpha. S Z beta is equal to H cross by 2 into beta. In earlier slide you have seen the role of S, and now the Sz with its Pauli spinors alpha and beta. So Sz alpha is equal to H cross by 2 alpha, Sz beta is equal to H cross by 2 beta. So H cross by 2 is the eigenvalue of this Sz. The alpha and beta are the simultaneous eigenvectors of S square and Sz. So here alpha and beta are with S square. Here Sz alpha and Sz beta is considered, and the eigenvalue of Sz is H cross by 2. So thus alpha and beta are the simultaneously eigenvectors of S square and Sz, and have the eigenvalues 3H cross square by 4 and plus minus H cross by 2 respectively. In case of alpha beta, here I have mentioned plus minus sign that basically signifies the spin up and spin down state of the particle. The components of sigma anti-commute, which means sigma x sigma y plus sigma y sigma x is equal to 0. The next yz component sigma y sigma z plus sigma z sigma y is equal to 0, and now zx component sigma z sigma x plus sigma x sigma z is equal to 0. So these components Pauli spin operator basically signifies the anti-commute properties. Further, we can show that sigma x sigma y minus sigma y sigma x is equal to 2i sigma z. Sigma y sigma z minus sigma z sigma y is equal to 2i sigma x. Further, sigma z sigma x minus z is equal to 2i sigma y. So when you are taking the xy component, here you are writing z component, y z, then this will be sigma x, z x, then it will be y, and multiply it with the 2i. So just to keep remember, you can prove it, and I will show you into the next slide. These things basically gives you sigma x sigma y is equal to I sigma z, sigma y sigma z is equal to I sigma x, sigma z sigma x is equal to I sigma y. So I am showing here this result sigma x sigma y plus sigma y sigma x is equal to 0. Actually these anti-commute these components. So sigma x, you know, that is 0 1 1 0, sigma y is equal to 0 minus I 0. So the result sigma x sigma y is equal to I 0 0 minus I after multiplication of these two matrices. And for sigma y sigma x, this is equal to minus I 0 0 I, and now the sum of these two components sigma x sigma y plus sigma y sigma x is equal to this matrix and sum of the second. So the result is this one, that is a 0 matrix. So result of it will be equal to a 0. Here sigma x sigma y sigma x, and now the subtraction of these two matrices, and result is this I plus I 0 plus 0 0 plus 0 minus I, and as a result you will get this matrix. Take out this 2i common, and as a result you will get this one, that is the sigma z. So 2i into sigma z, and further sigma x, sigma y you have seen, that is equal to this one. Take out this I common, and as a result you will get this one. So now by this way one can prove it. So this was the basic idea of Pauli spin formalism into the nuclear physics. Now next slide is about the parity of nuclei, how one can define the, in general we define a physical system with a notation of psi, that is known as a wave function, which depends on some coordinates, that is x, y and z in three-dimensional system, and can be written as psi as a function of x, y, z. 2 minus x, y is minus y, z into minus z. Then the wave function becomes psi as a function of minus x, minus y, minus z. Right, under the space inversion, if the Hamiltonian of the physical system remains invariant, its wave function will also remain unchanged. So the most important point into the parity is that when you are changing the coordinates, so psi minus x minus y minus z is equal to plus psi x y z. It means the parity is even. When by changing the coordinate from x y z to the minus x minus y minus z, and as a result we get this negative sign, then we say parity is odd. So in the case of a revolving particle in an orbit, the parity is defined by this formula, that is minus 1 raised power L, where L is the orbital angular momentum and its even values like 0, 2, 4, 6, 8, all the even numbers. If you put this value here in this formula, then you get positive result. So if you are getting positive result, it means parity is even, and if you are getting negative result, it means parity is odd. So for the odd values of the L, the parity is odd, and for the even values of the L, parity is even. So for the nucleons, neutron and protons, conventionally parity is even.